Thank you very much. Thank you, Dirk. And really great to be here. And sort of it's a little different from, it won't be specifically about economics or this type of questions. But I was thinking what is the connection? And it's kind of clear that now like LLMs and this type of methods are pretty much pervasive. They're like, you cannot escape them. And so what I'm going to talk about is work with wonderful students and collaborators with Daniel Beaglehole, Dima Drusvyatsky, Party Pandit, Adit Radhakrishnan, Neil Malinar, and Libin Zhu. So I think we have seen in the recent few years is that mathematics is literally transforming the world. Things which we couldn't even imagine were possible like only a few years ago, suddenly are possible, and not just possible, they're like being done all the time. And the strange thing here is that, LLMs are just mathematical formulas, and sort of unusually, I think historically, we don't really understand what they do, how they do it, and when they work at all. And I sort of tried to argue that without mathematical understanding of what these models do, there is sort of no hope to really be able to control them or to guide them in sort of any reasonable way. And I'm sort of, it's good to see that there is now much more work recently being done in the theoretical understanding of this model, although I'm sort of have become concerned that it's probably too slow given the pace of development of the things. In any case, so what is the key question here? I think the sort of fundamental question, and I think this is true throughout, is that we are faced with stimuli of high dimension. And really everything is high dimensional. Now, the question is, well, how do we make sense of this high dimensional world, given that in some mathematical, fairly precise mathematical way, intrinsically high dimensional spaces are not really, cannot be explored. And let me just give you a very quick example. Of course, we probably all know this. So if you have an LLM type model, like transformer type model or whatever, you're just predicting the next token given, say, a context size of, say, of length 4,000. And this is just a Markov model, so you're predicting the next word. And that's all you do, right? You just predict the next word, move the context window by one, and keep doing this. Now, if you look at the size of the dimension of this, so if you think about it just as a Markov model, that had some sort of gigantic matrix size, whose size is the number of different tokens, which is something like, say, 50,000, and the context size, to the power of the context size, which is, say, like 4,000 for GPT 3.5. Times the vocabulary size, which is 50,000. So you can see this is some sort of absurdly large number. Now, we think that we have a lot of data, because it's being trained on like everything in the world, but really the data is very, very puny compared to something of that size. It should be impossible to estimate anything like this from 10 to the 12 data points. It's like 1 trillion data points, a sort of realistic size of the data sets that we have. The largest ones, well, maybe 10 trillion. Okay, so what's going on? So what is the problem? Well, the fundamental problem, mathematically, you can say, well, we need, if we have a d-dimensional space, so something with d degrees of freedom, we generally need e to the d point to somehow explore that space. And, well, what does it mean? Well, given that we only have 10 to the 12 point, right, the maximum that we can have is log of 10 to the 12 points. So the dimension, the actual dimension of the language must be like 30. This is not just one language. This is like all languages in the world, or all languages with a sufficiently large written corpus. So 30 is pretty low, right? But where is it hiding? And so first, I think it became very clear that the language and many other, and presumably other processes, like presumably things like economic processes and so on, are probably very low dimensional phenomena. Second, we have to sort of, if we accept this point, well, what is a latent space? And what do neural networks do to somehow find a structure in the latent space? And can we use whatever neural networks do to build other models as well? And at the very least, for me, this is a very interesting question. So maybe in practice, people are just happy to do neural networks. So this is going to be based on, so this is a step maybe toward understanding some of these questions. It's going to be based on the three, primarily based on the 3 papers, and 2 of them are online, and the 3rd one is in preparation. Okay, so first, what do we have? Like, we can just think of all of this LLM. So I'm not going to talk so much about LLM specifically. Just think about a simple, so actually LLM is just a prediction model, right? Okay, we predict the probability, but we can just predict the next token and just take the highest probability token, that's it. Then it's a simple prediction, multi-class prediction problem. Can we, well, does it matter that we sample from it? Yes, it matters to some degree, but if you just predict the next token and choose the most likely one, it's already okay. So what do we have? Well, given this input, we just want to predict the output. This is a very standard classification sort of regression problem. So you have some feature space X, you have some sort of hypothesis space H, and you want to, given your training data, you want to select some function f from H that it will predict well on future data, right? That's a generalization. Okay, so now what is this? You can kind of think of dimensionality as being like on 2 sides of this diagram. On one side, we can say, well, okay, maybe we want feature space to be low dimensional, and there are like all sorts of classical methods for that, like PCA, MDS, and so on. More recently, things like manifold learning and nonlinear dimensionality reduction. On the model space, there's been a lot of work on certain things, sparsity, trying to find some sort of, say, a small set of predictors which describe this function space, or maybe just controlling the number of parameters, so then very classically, of course, controlling the size of the model, or controlling maybe the norm instead of the size, which has a sort of similar effect. Now, what we have in modern practice, so we see that basically, yeah, X is probably very high dimensional, and H is some gigantic parameter space, like maybe 1 trillion parameter for this large model, something of that order. And basically, it's all okay. Don't worry about it, right? That's what they tell us. Well, obviously, the proof is that these models work, and there is like no explicit, at least, regularization, or very little explicit regularization. And sort of what we have seen is that just more parameters is just generally better. So let me now kind of take a step back and describe a pretty classical method, the kernel machine. I'm not going to do it in any depth, just to sort of remind you what it is. And if you're not familiar with this, you can just assume that it has a nice solution. So you have your X and Y, and you have some class of functions H, which in this case is a reproducing kernel Hilbert space. And then you're trying to optimize basically the loss. And with the key algorithmic insight there is that for certain classes of H, you have this beautiful direct representation that the solution to this gives you, is given by sum of the kernels, and by kernels you can, for example, think just sum of Gaussian. It's a mixture of Gaussians. And each Gaussian is centered in one of your data points, and the coefficients for the thing can be found, that's why I put the square loss, it makes things simpler, can be found by simply solving a linear equation, or linear system of equations. So you have this very nice explicit solution, And okay, well, this goes back to splines in kernel machines. And actually, very recently, we understand now that wide neural networks trained with gradient descent, in some, at least, settings are also given by these models. So this, when I thought that, of course, I was, I was very happy because, like now we have like very simple model of what these neural networks do. And this goes back to this kind of classical setups. It turns out things are much more involved. And that's why I kind of emphasize that this is under certain conditions. And these are not the conditions which are, in fact, realistic, sadly enough. So what is happening is that what is special about neural network? Well, on the H side, we kind of now understand that having a lot of parameters is okay, and kernels are, in some sense, infinite parametric models already. However, on the X side, it looks like neural networks seem to have no issue with high input dimension. They just do some sort of dimensionality reduction and then some sort of automatic process. And the question is why? And sort of the answer, what I'm going to suggest, is that neural networks learn relevant directions. And I'm going to describe what relevant directions are. I mean, this doesn't, of course, explain like everything which is happening in neural networks, but I think it's, at the very least, it's a step. And so what are these relevant directions? And let me just, I'm going to run through like a few simple experiments, or not so simple, I don't know. Relatively simple experiments here, and just show you the results and sort of try to give some intuition about what's happening here. So imagine my X is just a normally distributed random variable, okay? And now Y is, I take the sum of the first 5 coordinates and times the sum of the next 5 coordinates. So that is what known as a, so if you look at the sparsity of the thing, well, it's a polynomial of degree 2 in, 100 dimensions. But if you look at like 10 sparse, but actually even better, it's what's known as an index 2 model. And what is an index 2 model? Index 2 model is, it just depends on 2 linear directions. What are the linear, oops, sorry. The linear directions here is the sum of the first 5 variables and the sum of the second 5 variables, okay? So it's some matrix of rank 2 applied to your data, a projection onto a 2-dimensional space, and then you have some sort of non-linearity on top of that. Now, okay, well, I take 4,000 training points, and we apply Laplace kernel. So Laplace kernel, for the purpose of this, is just a Gaussian without a square. And that seems to work well in practice. And what we see with Laplace kernel is that a neural network does with a R squared. So R squared being 1, of course, is good, and 0 is bad. So for Laplace kernel is 0.25. For neural networks is 0.98. With neural network here, I mean just a very simple basic neural network 2-layer. What does it mean? That means that somehow whatever neural networks do is very different from what the kernel does, right? It's very clear, I think, from this example. And there've been work recently that we will try to understand this, and in particular for, for this low index model, like multi-index models, what this is called. We can now prove that neural networks you trained using gradient descent do something which is different from kernels. What's amazing to me is that the first result actually this is an experiment, like the first experiment of this type was done like only 6 years ago. Even though this is such a simple setup, kind of slightly disturbing. Okay, be it as it may. Let me first tell you maybe like one way to think about it. So suppose you have a neural network, and again, I just mean a fully connected neural network here. You can just think about 2 layers, but any number of layers would be okay. You have, so how does it work, right? You have the first layer, like you have the input, you apply some matrix W1 to it, and then you apply some sort of nonlinearity on top of that. So let's not worry about the nature of nonlinearity, let's just think about W1. So you can think of W1 as somehow a filter of your data, so it takes some data and it filters something out, or filters something in for that matter. Now, W1 is a little inconvenient to think about, but you can think about W1 transpose W1, which is a matrix which takes sorry, I'm not used to this thing, which is a 100 by 100 matrix. It's a transformation of your 100-dimensional space. Now, the intuition here is to think of a trained neural network as basically a low-rank filter given by this matrix, followed by some sort of nonlinear predictor. And let me sort of try to convince you that this is really what happens, at least for that simple setup. Before that, I need to have a different mathematical object, which is known as average gradient outer product. And this is the following thing. So suppose you have some model now, F. And I will construct the following mathematical object. I will take gradient of F with respect to the input. So with respect to the input, it's very important here. It's not with respect to the parameters. I don't care about parameters for this at all. With respect to the input, at every data point that I have, and I'm going to take the outer product of the gradients. So if you think about what outer product means, you can kind of think this as a projection onto the direction of the gradient at every data point. And for multi-index model, you can think that if M here is low rank, then the span of the, well, say, I guess, row span, you can think of row span of M, is the same as the span of the AGOP. So if you can find this AGOP matrix, it will recover effectively the span of the matrix M. It will recover its range. So, or you can say it another way, the top eigenvectors of this AGOP matrix align with the range of M. Now, why is this good? Well, because this is presumably if it's low dimensional, and if I can somehow estimate this, this would be great because I can go to this much lower dimensional space. And if you think about what this does, you see, if a direction doesn't change my output function, I don't care about that direction. So I only care about directions in my input which has an effect on the output. So that's what I would call like relevant features. If a feature is irrelevant, just ignore it. And so the trick is, well, how do you find irrelevant features given that you don't know anything about your data? And let me, I think I'll skip this. Let me now go back to this example and look at what this thing finds. So remember, I have this W1 transpose W1 matrix. And now I'm going to show you this W1 transpose W1 and compare it to the AGOP. And what you can see is that these two little squares on top, they correspond to these 5 by 5 blocks. So in this model, once you run a neural network and you train it on 4,000 samples from that distribution, you actually see that the filtering matrix and this AGOP matrix actually identify that subspace. And in fact, as you can see, they're almost the same. At least visually, they look the same. Not the same, but very similar. Now, here is the interesting thing now. So here is the experiment. Now, let's train a neural network on 4,000 samples on that simple model. And then I'm just going to keep this matrix, one of those two matrices, and I'm going to discard the result of training the neural network. So all I did in my training of the neural network, I just found this filter. Now, if I use this filter, and I now train a kernel machine on top of that filter, I can see the results are actually very good. So remember, in the original problem, my kernel pretty much failed. But if I use it after I filter the data, it succeeds. Okay, and if there are any questions, I'm more than happy to answer because, yeah.
If I were to evaluate the similarity of those two matrices, not visually, but maybe by subtracting them and taking the spectral norm of difference.
Perfect. Perfect. Next slide. Oh, 2 slides actually. Thank you. Right now, I'm just claiming that they're visually very similar. But you can also see here that the result by filtering one or the other is pretty similar, not exactly the same. But so basically, once I use one of those matrices and I use it as a filter, kernel and neural network actually do about the same. Actually, kernel does slightly better. But if I don't use the filtering, kernel completely fails, and neural networks mostly fails. Why? Because it's only 500 training samples, right? But those filters are obtained with much more data. So the claim is that like what neural network is doing, it's actually a lot of it is just learning that filter. So maybe that's like one message to keep in mind. Okay, now here is the so I claim that visually the things look very similar. So we actually claim that this is a general pattern. And these two matrices are almost the same. When now I'm thinking they're approximately proportional to each other. So it's an empirical fact, it's not a theorem. We can prove it in some very special cases, but in general, they're definitely not quite the same. But yeah, we call it the neural feature ansatz, because it's some sort of ansatz, it's like in physics, it's like a simplifying principle. And you can do it actually for any layer of a neural net. And now you can evaluate this numerically, the correlation. And you can see, well, the correlation is not perfect, but it's like very consistently above, like around 0.9. And this actually holds, so I made all these claims about MLPs, but this holds for convolutional neural networks, and in fact for like pretty much, as far as we can tell, this is general to any sort of practical architecture. For transformers in particular, for even things like recurrent neural nets. You can see they're not always like very high, but even in these cases, they're like 0.7, maybe 0.6. That's the lowest. But usually they're much higher, like 0.9 or so. Okay, so now actually this is kind of interesting because this gives you some sort of idea between this AGOP, which is some sort of external evaluation of the net, and this internal structure which is being learned by this very opaque and complex process of stochastic gradient descent. Now, you can actually kind of have a little bit of fun with those matrices. You can, for example, do, you can take one of those matrices, right, take these eigenvectors and find that certain concepts which align with some of this eigen. This is for GPT-2 trained on tiny stories. It's like a small data set. You can see that like some of these eigenvectors align very nicely with like things like names or adjectives and so on. So you do recover, definitely you recover a lot of semantic or syntactic information from that. But let me maybe make, so this is maybe like a kind of step toward what they've been calling mechanistic interpretability. In any case, let me kind of move forward maybe and like suggest what can we do with this? Like, why is this a useful thing? And so far, this is some sort of connection between two different types of structure that you can extract. But what can we do with this? And the claim is that like once, if we really believe that this is the right thing, that this object that we extract is the right thing, well, we can just like use it. Well, how would we use it? Well, let's think about it. I sort of claim that neural networks are basically like kernel machines on top of learning these relevant features. And these features are given by this mathematical object, the AGOP. And you can kind of think, well, what does AGOP do in this case? It's some sort of linear transformation of my input. And then this question becomes, well, can we learn both the kernel and the linear transformation of the input? So in this case, we want to learn like the matrix M. That would be our filter. Well, how would we do this? Actually, the method, we call it recursive feature machines, it's sort of maybe the most naive thing that you can do. So what you do is the following. You build your predictor, so start by building your predictor the usual way you do. And then once you have this predictor, you can simply, you have an analytic form of the function, right? And then you compute the filter based on what you already computed. Okay, and maybe this is garbage, but let's just try. So you have this, then you compute this filter, then you filter the data, and maybe using some power. I don't really want to discuss like why would you choose like different powers here? Not right now, at least. And then once you refilter the data, you can recompute your predictor. Okay, so it's kind of a loop and sort of EM-like procedure. And you sort of hope that like at every iteration you learn a little bit better because you somehow like filter the data, get rid of a little bit of noise maybe, get a little bit better result, and your next iteration filter will be better than the previous one. Okay, okay. Now, this is actually what it turns out to be mathematically for, specifically for the Laplacian kernel, which seems like a good choice of a kernel. Now, let me maybe instead of sort of giving mathematical formula, let me give you a very simple example of what it does. This is a kind of synthetic example, but it's nice that you can visualize it. So just embed like a little star here, and the color of the star encodes, so these are trucks, these are images of trucks and planes, and the color of the star encodes which image it is. Okay, so for, if you know where to look at, right, like a single pixel would be enough to figure out that it's a plane or a truck. But if you actually don't know where you look at, this is a hard problem. So if you train a neural net on this, you see something quite interesting. You see that after about 80 epochs, the training accuracy is already close to 100%, but your test accuracy is still pretty bad, right? It's only at about 70% or 75%. And if you visualize that matrix M that I had before, which is W transpose W, you can see that there is like a little star here, but it's very, very noisy. As you train the neural net, you can see that the accuracy on test just keeps improving, even though training accuracy is already 100%. So this is like actually one of the important points, is that training accuracy and test accuracy are really not related. This has very little to do with optimizing the... So it's a weird thing, because the loss function, you think that you're optimizing the loss function, but you're actually doing something quite different. And yeah, question? This is just standard SGD. Yeah, very, very standard stuff. Yeah. And you can see that after about 150 iterations, epochs, your star is much brighter here, and you'll get like 98% or something like that accuracy. So you're really like, what you're doing is really learning the filter. You are not optimizing anything. Well, you are, of course, optimizing the loss function because that's the only thing you can do. But the result that you get is because this optimization has some sort of side effect, which is learning these features. Now we can use our method, and actually with our method, after it's even, you know, like more striking because before after you just fit a kernel, so at 0th iteration, your accuracy is 55%, okay, really terrible. But you already see that you identify the features quite well. So even though the input is it's like nearly garbage, but you can learn the features. And after one iteration, it becomes like 90%, and then it becomes 100%. So you're very quickly converging to this. So you can see that every iteration here is like maybe 100 epochs for the neural network, something like that may be the way to think about it. So I think a kind of upshot here is that feature learning in neural networks is really distinct from fitting training data. I think there's kind of a misconception with, at least like in our community, we have been sort of really dealing with for many years. In sort of machine learning, like learning theory. Loss is not a proxy for accuracy, that's another thing. And nicely enough, RFM, our method, decouples feature learning from optimization. Because if you can see, RFM is trained to have 100%. It's actually numerically exact, it just fits the data. There is no, the accuracy is kind of trivially 100% because you just fit the data exactly. I will give, I hope I have time, I want to give actually an even more striking example of something like that, but much more striking than this. Okay, so, well, we will run it actually on a bunch of data. It is, in fact, it's state-of-the-art on tabular data. So it works quite well. But maybe let me sort of say a few words about something else, and then I want to go back to the feature learning. So I apologize about this kind of non-linear flow of the talk. Oops, why is it? So, okay, well, let's think about a very different problem. And this is a problem of, so suppose you have a matrix. So the classical one is, like movie ratings. And you want to rate a new movie, right? So you have a bunch of examples. So you have a big matrix with a bunch of missing entries. And you would like to fill it in. Well, how do you fill it in? Well, in general, it's an impossible problem to fill in a matrix. But suppose you assume that this is a low rank prediction. So that's how low dimensionality comes in, right? There is some sort of low rank. And because maybe like certain types of people like certain movies, right? That's kind of some sort of low rank structure. Now, how would you do it if you think that, what would you do? And the sort of classical idea here is something known as something called the nuclear norm, which is simply the following. You take eigenvalues of this matrix, and you take the sum of absolute value of this well, singular values, but whatever. So it turns out that this nuclear norm actually leads to low rank completion, and this is provable under some conditions. And second, that there is some sort of nice way to do it in a that actually turns out to be a convex problem, which is not obvious. So that was a sort of big realization some 10 years ago or so. And the interesting thing, and maybe I would just like to bring this up without discussing this too much, is that the method that I just described, if you set up the correct way, with your kernel just being linear, so it's kind of like two-layer linear thing, right? There is some transformation and then some linear predictor on top of that, is in fact a generalization of a classical method to do just that, which is known as iteratively reweighted least squares. So you get low rank matrix completion in some sense for free from this thing. And I'm not going to tell you exactly what the method is, but maybe I can just tell you what the theorem is. So when you apply that method, you observe some matrices, and you observe some entries of a matrix. And what this matrix gives you, or what this method gives you, I should be a little bit more precise. So we cannot prove that it converges to this. We can only prove that this is a fixed point of the iteration. But the fixed point of the iteration is the is a matrix which is consistent with the observed entries, but has a small, say, L1 norm of the eigenvalues. Okay, so more general than L1. It's actually not a norm at all. So you basically have some sort of penalty norm on the eigenvalues and on the singular values. And what we can show is that this is the same thing that our method finds. Okay, why is this interesting? Well, this is interesting for several reasons, but for one reason is that this is actually what has been observed for depth L linear, for deep linear networks. And interestingly enough, you can even like generalize this for L deep neural networks when L is equal to infinity. That corresponds to some parameter in the model. So you can kind of usefully think about like what would infinitely deep network do? Funnily enough, you can take this parameter bigger than 1/2, and then it becomes negative depth. Neural net, whatever that might mean. Okay, but let me now kind of take a step back to feature learning from this. And I think there is, in the last maybe, what do I have, 5 minutes? 7 yeah, minutes, so, yeah. Oh, perfect. I would like to discuss, well, there is a sort of more basic question in a sense. Is there some way we can predict generalization in machine learning, or are these properties emergent? And sort of recently, there have been a lot of arguments saying that, well, if you take a sufficiently large neural network and you train it like long enough, then it just suddenly like learns stuff. Like these properties really emerge and you cannot predict them before you somehow like complete training. And I personally, I've been always a little skeptical about this because like, what is this magic? I mean, it sounds completely magical. And well, let me kind of discuss one example of behavior like this. But notice that this is something, I worked at, is that we already kind of discard it as a training loss, which is not predicted. So we know that training loss is not predictive of generalization because if your number of parameters is large enough, so on the x-axis you have a number of parameters and on the y-axis you have risk. And this kind of, the solid curve here is the risk on training. You can see that you can have the test loss very small. But the training loss is, well, the test loss here is actually 0. But the training loss is not 0. So you cannot really tie those things together. And that has been sort of now well established. Now, what I'm saying with the emergence is something even more striking. Is like, well, not just the training loss, can the validation loss, so my answer was like, well, if people ask me like, what do you do? Well, you look at the validation data set and you see whether you get a good result in validation. But what this emergent thing is saying is that maybe even validation is useless. And let me give you an example. This was from the Grokking paper, 2022, just 2 years ago. The problem was to learning modular arithmetic. So you have like, say, mod 5, like, 3 plus 3 equals 1 mod 5. So you give examples of these pairs, and then you try to make it predict what the output is. So essentially, this is filling some table like this. Now, what they observed is the following. So you train a neural network, and you have this number of optimization steps. And you can see that the accuracy on train, which is a red line, fairly quickly becomes perfect, right? So you have perfect training loss. Well, in this case, this is training accuracy, but you can think the loss actually has the same shape. But the test accuracy is still at random. It's basically 0. Well, this is like mod 100 or something. So, like your random prediction would be 1%, right? If you just choose a number at random. If you're trying to predict something mod 100 and you choose a number at random, it's 1%. So now what do we have here? We have this green loss, the green loss curve, which is 0. And then at about 10 to the 5 steps, it suddenly just jumps to 100%. They called it grokking. And they actually said, look, like, how can you possibly predict this behavior? Because you're already perfect on, right? You're already perfect on train. And you are still not doing anything on test until this point, which is 3 orders of magnitude more steps than what you need to get to perfect train accuracy. And well, let me show you the analogous thing with our method, which I think is even more striking for several reasons. It's a very similar curve. What we do is exactly the same problem. And, oops, I don't want this yet. What you see is that, so your training loss is 0, both accuracy and loss here, you can just think, accuracy is 100%, loss is 0. And you can see that after about 5 iterations, your loss hasn't changed at all. The accuracy is still at random level, right? So your loss is whatever it was in the beginning, which is basically just garbage. And then after about 10 iterations of our method, you suddenly have this very rapid rise, and you get perfect prediction. So exactly what they had before. There is, however, difference. The difference is that for us, there is no, when you train a neural network, your training loss is never quite 0. So you may think, well, maybe like once the training loss drops below some level, you get this sharp transition. For us, the training loss is identically 0. So from an optimization point of view, you are perfect even at the first step. But you have no generalization. And generalization seems to appear out of nothing. This, to me, was like, I was actually like kind of shocked by this. Because now I don't know, like, what do we look for? Now you can look at these learned feature matrices that we have, and you see that the structure actually slowly emerges. And it emerges, you can see that even after 1 iteration, you already have this striped structure, and the stripes becoming more and more prominent. And after about like 10 or 15 iterations, you can see they're pretty much perfect. So these are circular matrices. So what you can see is that you can actually compute this, and you can check, yes, it gives you circular matrices. Circular matrices actually make sense for this problem because they're somehow related to the algorithm that the thing learns. But that doesn't really, this is still very much a post hoc explanation. So post hoc, we can explain this quite nicely. But how do you know that this is what you need to do before you learn this problem? So I don't think right now we have any way of actually like having generalization. So let me maybe summarize this, and then I'll have a couple of thoughts about the whole thing. So first, we can see that we learn actually the circular features, and it corresponds to this Fourier multiplication algorithm, which is kind of cool that the thing somehow learn this algorithm. Not specific to neural network or gradient-based methods, so I don't think we should think of neural network doing something that's special. The special thing is that they're learning features. And we can get the same behavior with this very different architecture. Simpler to analyze and maybe simpler to implement for other problems as well, but definitely simpler to implement. Now, generalization is not predicting by test or training loss. It's, as far as we can tell, it's not predicting by anything. Like, I really have no idea now what would be a good predictor of generalization. I think there is a strong evidence for emergence. There was like a paper, for example, which won, I think, New Reap's Best Paper Award, which said it was a mirage. It's clearly not a mirage. This is, like, obviously real. The argument was that you can look, that this emergence results from a disconnect between discrete accuracy and continuous loss. But in our case, the loss and accuracy are both perfect, so there is no disconnect. So obviously, in this case at least. It may be a mirage in other cases, but not in this case. Okay, so let me conclude. Well, I think data are just far, far more predictable than we thought. This is, you know, has been kind of an amazing finding, one of the great findings, I think. Neural network, I'm arguing, implements some sort of task dependent dimensionality reduction, and I think we should kind of take the lesson that basically the trick is to make all learning supervised learning. That has been very consistent pattern in a lot of these methods. Now, feature learning, I think, truly a mysterious process, and because even for this kernel, very simple kernel setting, we just don't understand like what makes it. Because if your loss doesn't improve, why do your features improve? This is not clear at all. Where is the signal? It looks all like noise, it's all garbage, it's all at random, but yet the features keep improving, and once your features improve enough, you get this emergence. Like, why? No, I think we don't even know this, and we have no useful predictors of generalization, so I'm sorry, this is kind of a negative message. Finally, I would like to say that I think RFM, the recursive feature machines, provide both practical and theoretical framework, which really simplify thinking about a lot of these problems. And nicely enough, they recover these classical algorithms. We need some sort of, I think a lot of what we do needs to be sort of very physics style, that we should observe things and we should look for some sort of mathematical descriptions, but not necessarily rigorous theorems. And it's very clear that any generalization without feature learning is probably not good enough. And I'll stop here. Thank you.